my pleasure today to share this third webinar with Thierry Bruminel. So I will introduce our first speaker, Xiaomeng CUI. Is an associate professor at the Institute of Economic and Social Research at Jinan University in China. He obtained his PhD in agricultural resource economics at the University of California, Davis. I think it was under the supervision of Pierre Merel, who was our first speaker at the first webinar. His research interests include environmental and resource economics, agricultural economics, and he published several papers on these topics in top field journals, as in JIM or in the American Journal of Agricultural Economics, as the paper he is presenting today. So the paper of today is not really on intensification, but it's on adjustments during growing seasons. So we will tell us a little bit more about it. You have 30 minutes. The floor is yours. Thank you.
Well, thanks. Thank you very much. Let me share my screen. Yeah, can you see my screen?
Yes.
Yes, no problem.
It's showing my slides, right?
Yes, absolutely.
Okay, cool. So thank you very much for this invitation, and I'm very glad to talk about this recent research I have done with my co-author Wei Xie from China Center for Agricultural Policy at Peking University. And in this work, we in particular look at a specific adaptation or adjustment margin this growing season. And we look at the specific context of corn planting in China. And just to first sort of give you a broader motivation of this work, we know that climate change poses a lot of threats on global food security in the future. And as myself, as an empirical economist, we have seen a lot of recent work by using panel estimation to examine how climate change really affect agricultural production, especially on crop yields, and been listing some of them here. And there's also discussion on sort of a potential lack of adaptation. For example, Marshall Burke and Kel Emmerich recent paper discussed there's a limited adaptation in corn and soybean yields in the United States context. And when we look at this literature from sort of a econometric perspective, a common assumption in this sort of modeling work is that the growing season is typically assumed to be fixed when doing this type of panel estimation. And there's a practical reason for doing this, and sometimes it's justifiable. But the remaining concern or question is how much could farmers actually adapt to or adjust through changing their growing seasons? And if they do have this channel of adjustment, how does that translate into sort of implications on crop production or crop yields in general? And when we look at the literature, even just the economics literature, there have been some discussion on this potential channel, but mostly through the practice of hypothetical simulations, which we call that this way. The table I'm showing you here is sort of an example. That's from a work by Ariel Ortiz-Bobilla and Rich Just I think on AJAE papers and proceedings about 10 years ago. So what they look at is that hypothetically, if farmers are sort of adjusting in the optimal way in terms of shifting their growing seasons, how would that mitigate the potential yield losses associated with climate change? And if you look at their estimates, for example, in Pennsylvania, about 70% of the yield losses associated with climate change can be mitigated by simply shifting the growing season forward. But this is not based on something actually happens, more like a hypothetical best and optimal adjustment. But we don't know in reality to what extent can farmers really adapt or adjust in this way. And we also survey some literature, and there's certainly in the scientific community, and there's a group of phenological studies looking at sort of the correlations between warming trends and earlier planting date or planting time. And when we look into details, we feel that from an empirical economist perspective, we feel that they're still lacking a causal interpretation of the results, since a lot of most of the time the correlation is established by simply correlating the trends in warming temperature and the trends in earlier planting time. But there could be potential confounding factors that's driving the spurious correlation. That's not really the causal link there. So all of these motivate our work is we wish to understand by using these modern econometric tools to have a causal interpretation or causal identification on how do farmers in reality adjust growing seasons in response to temperature and precipitation. And building on those estimates, we wish to understand what's the implication of those induced growing season adjustments. And just to first give you a quick preview of the main findings, so we use a micro level crop progress data that's sort of novel data set, and covers about 800, this is called agroclimatic monitoring sites in China, which I will talk about them in more details later. And we focus on corn, and we explore two margins of the growing season adjustment. One is the planting time, and the other is the length of growing season. And we use a panel fixed effects estimation framework so that we sort of explore the exogenous variation in weather within the site of the monitoring sites. And the general finding is that higher pre-planting temperature and precipitation is going to advance the planting date, and higher post-planting temperature and precipitation is going to shorten the growing season. And we also have a set of back of the envelope calculation, or you call simulations, that show, for example, for the median site in our sample, by the end of this century, under projected climate, this climate change will induce about 2 to 6 days earlier planting date. And on top of that, there's going to be another 3 to 6 days shorter growing season. And if we further translate that, those growing season shifts into a potential yield benefit, we find that this shift can avoid up to 9% of the detrimental impacts on corn yields that's associated with the changing climate in the future. So those will be the main finding of the paper. I'm going to focus on those main findings in today's talk. In the paper, we also have some additional discussion on sort of identifying the long-run adaptation directly and trying to look at accompanied input adjustment, although we don't find significant evidence on those parts. And also we have discussion on regional heterogeneity in the paper, but I probably won't have time to talk about those things in details today. In terms of the contribution of this work, so we think this provides a causal estimate of the temperature and precipitation effects on growing season adjustment, and it contributes to the understanding of climate change impacts on agriculture. And there's a long literature and still emerging growing literature on this. And more specifically, since we are looking at the Chinese context, we think this extends our understanding on climate change impacts on Chinese agriculture specifically, since there haven't been a lot of discussion on this in terms of the country focus. And in terms of implication of the results, we think this paper sort of brings up some reassessment of the projected yield losses and their future climate, especially for those panel estimation that assumes a fixed growing seasons. And our results is sort of qualitatively similar to those hypothetical simulated results. For example, the table I showed you before, but quantitatively, the results we find is much smaller, and we think this reflects the potential obstacles in sort of optimally adapting this way in practice. And this paper also builds on the emerging literature on understanding environmental adaptation or agricultural adaptation to climate change in general. And then this also includes some of my earlier work on planting acreage and crop abandonment. This is generally an empirical work. So let me introduce the data set we put together to make this empirical examination feasible. So the main data set we use is a crop progress information. And this is based on nationwide agroclimatic monitoring sites. And those sites is a network established by the government, and the purpose of the sites is to monitor the condition or the situation of the growth of crops in different places in the major agricultural regions in China. And the way it works is that it's not the site is run by government staff. Those fields of the sites are still managed by ordinary farmers. The purpose or the function of the site is really just to monitor, and they're not really interfering the actual agricultural practice there, so that the practice there should be representative of ordinary farmers. And the sites are selected in a way such that those sites will represent the surroundings of the location. And this is a partially confidential data we sort of use under contract with National Meteorological Information Center of China. And the specific information in the data sets that for each site, there's going to be specific information on the planting and maturity days of a specific crop planted at the site, and we recorded for every year within the sampling period. And because we focus on corn, so eventually we will have about 260 sites in our sample. And the weather information is based on those nationally certified weather stations. And there's roughly 7 stations all over China during that sampling period. And the typical information recorded at those stations will just be daily maximum and minimum temperature, and also daily cumulative precipitation. Those are standard information. And those weather information and the crop progress information are sort of 2 separate data sources. So we need to match them. And the way we do this is just to do an interpolation over space. So we use the inverse distance weighting to interpolate the weather information to the agricultural monitoring sites. And this is also the standard practice in this literature, especially for using Chinese data. And we also have some additional data on different agricultural zones, and also on some county level information on inputs, but I probably won't have time to cover those details. This is a map to show you sort of the major data sources we use. And in this map, those small crosses are the location of weather stations we used in our study. And those round circles are the agroclimatic sites, the monitoring sites we have information for crop progress. And those in red color are the corn sites we used in our sample. And just to give you a context on corn production in China, this map I borrowed from USDA. It just shows the sort of distribution, spatial distribution of production shares by different provinces. And most of the corn production is in the northern region, and especially the northeast. And sort of this distribution is similar to the distribution of those red dots I show you here in terms of the data we use. And let me go to the estimation. So the estimation, because we look at 2 separate margins, one is the planting time, the other is the growing season. We do this analysis separately for the 2 margins. First, I'm going to talk about planting date. So here, the idea is that it's still a standard panel fixed effects estimation. And the outcome variable PD here is just the planting date. And we have that information for the same site over years. And the way the variable is measured is the number of days since the first day of the year. So that smaller number means an earlier planting date in that year. And the key variables here are temperatures and precipitation. It's slightly complicated, but so let me introduce. This is going to be a set of, let me just first focus on the temperature variables. It's going to be a set of weekly average temperature. And if you look at the subscript of the variable, this mi minus j, this mi represents the normal planting time of this site I, and this minus j means the jth week before this normal planting time. And we are going to trace out this different weeks in the weeks before the normal planting time, because the idea is that the pre-planting weather is going to affect the planting decision. And it's a similar definition for the precipitation variables. It's also weekly cumulative precipitation, and it also indicates a set of weekly precipitation that's before the normal planting time of this site I. And the additional control variables, we have regional trends here in this H function. It's just a quadratic trends by region. And then we also have this important site fixed effect. So that capture all the time invariant site characteristics, and then the error term here. So in practice, in terms of tracing the weekly averages, we trace up to 12 weeks, so roughly 2 to 3 months before the normal planting time of each site. So this shows you the results in terms of the temperature estimates. And the way you interpret this figure is that so each dot is going to be a point estimate, and each line is going to be the 95% confidence intervals. And each dot is going to be corresponding to a specific week. And the week is indicated by these labels on the horizontal axis. So for example, for this first dot, it means that if the temperature, average temperature in the week before the normal planting date, a 1 degree Celsius increase in this week's temperature is going to induce about 0.2 days earlier planting date. That's the interpretation. And you interpret in the same way for the rest of the coefficient. The general pattern tells you that when it's closer to the planting time, warming is gonna induce earlier planting days. But when it's relatively farther away from the planting date, then the effect is not significant. In terms of the magnitude, for example, if we look at the first 5 weeks, suppose there's uniform 1 degree warmer temperature over the 5 weeks before the normal planting date, that's going to roughly translate into a 1 day earlier planting date. So that's the interpretation. And similar interpretation for the precipitation coefficients. And notice that the scale of the y-axis here is slightly different. But the general pattern here is that over roughly in the 4th to the 6th weeks before the normal planting time, if there's additional precipitation, that's going to induce earlier planting date. But compared to the temperature effects, is much more noisier since most of the confidence interval is overlapping with the 0 line. And this is flexible since we can trace out like weekly difference across time. But the downside is that for neighboring weeks, the correlation between weather variables will be high, so that our estimates are not that precise. So we also do a alternative estimation strategy. So the general idea is still the same. The only difference is that we are gonna, in this estimation, we're gonna combine every 4 weeks so that we have more precise estimates. So for example, this beta 1 is gonna capture sort of the average effect of the first 4 weeks before the planting time. And in addition to average temperature, we also use or consider 2 different measures of temperature. One is degree days. Here, the degree days is just a simple definition of degree days cumulative above 10 degrees Celsius. This 10 degrees comes from the technical report on sort of the triggering temperature for growing corn in China. And the third measure we look at is non-freezing days. So we define it as the number of days with minimum temperature above 0 degrees Celsius. So in this table, I'm going to report the regression results based on these 4-week version estimation for the 3 different specifications using 3 different types of temperature measures. The precipitation measures are all the same across different specifications. And the way you interpret these estimates is that, for example, if you look at this first estimate, it means that if the first 4 weeks before the normal planting time, if the average temperature goes up by 1 degree Celsius, then the planting date will be advanced by about 0.75 days. That's the interpretation. And when it's further away or even earlier away from the planting time, this effect becomes smaller, and then eventually it just disappears. And sort of qualitative similar story when we use other variables like degree days or non-freezing days, although the specific magnitude of the result will be different, since in the first column we measure temperature in terms of degrees, the second we measure in terms of degree days, and for the third we measure in terms of the number of days. So the magnitudes are not directly comparable, but they're still suggesting the similar general pattern over time. And for precipitation results, they're much more noisier, and we only have 1 significance at the first column, where over the 5th to the 8th weeks before the planting date, a 1 centimeter higher precipitation in terms of weekly cumulative precipitation is going to induce about more than 1 day earlier planting date. But this significance actually disappear when we move to other specification. So most of the results will be on the temperature effects here. And this is for planting date, and for the growing season length, it's still the same logic, although we need to adapt the estimation to the specific context. So here the outcome variable is GS, represent the length of growing season, and it's measured as the number of days in between the exact planting date and the exact maturity date in the same year, in the same growing season. And the in terms of the variables, we still have a set of key, temperature variables and set of precipitation variables, but now the variables are not the weeks before the planting date, but rather the weeks after the exact planting date, because those will be the weather information that's directly relevant for influencing the length of the growing season. And then here we allow for up to 24 weeks after the actual planting date. This number is just referred to the normal length of growing season in our case. And then as before, we have these regional trends and also site fixed effects to control for things in the background. And the results is like this. So this is still showing you the temperature results under this weekly average specification. And the general patterns here is that for the early part of the growing season, warming or higher temperature in general is gonna shorten the growing season. But when it comes to sort of the late stage of the growing season, this effect turns to be noisier and also in the opposite direction. That's the general pattern. And a similar story for precipitation here. In the early part of the growing season, higher precipitation is going to have a function in terms of, or in a way of shortening the growing season. But when it moves towards the end of the growing season, thus effects turn to the opposite direction. But if we look at the sort of the net effect or the aggregate effect, the early season effect is still going to be the dominant factor, both for temperature and precipitation. And also to just have more precise estimates, we also group every 4 weeks for this growing season length estimation. And this report, the results is reported here. And in addition to average temperature, we also have this degree days measure as an alternative temperature variable. And the third variable here we use is no longer the non-freezing days, but rather the hot days. Here, the hot days is defined as the number of days that's above 30 degrees Celsius. So just try to capture the days that's really hot. And the results here, if you look at those estimates, for example, if again look at the first estimate, it means that in the first 4 weeks, right after the exact planting date, a 1 degree higher average temperature is going to induce about 0.9 days, roughly 1 day, shorter growing season, and a similar impact for the for the first 12 weeks. Then this result started to slightly reverse when it comes to the later course of the growing season, and a similar pattern for precipitations. And this general pattern this doesn't change when we change the temperature variable we use. And it's very important to sort of contextualize how does this factor into sort of the long run impact or future climate. How does this induced growing season adjustment affect the actual production or actual outputs? So the way we try to contextualize this is we are going to combine our growing season estimates with a set of climate projection models. So here we use 5 different climate projection models under the CMAP5, and these models has been recently used for analysis on China. So we think this is appropriate, and we consider the RCP 4.5 and the RCP 8.5 as 2 different scenarios. So we were going to have 5 models with two scenarios, so 10 model scenario combinations by the end of this century. And for current climate or the baseline climate, we define this as the 30 years, referring to the sampling period we have, because the last year of our sample in the crop data will be the 2013. So we have this baseline climate defined as from 1984 to 2013. So the change from the baseline to the future will be the change from this period to the end of this century. And the climate projection model we use is based on monthly frequency. So we need to, so let me first show you this. This is just by calculating, based on the monthly frequency data, we calculate sort of the change in the climate under different model and under different RCP scenarios. So on top are temperature changes, and on the bottom are precipitation changes, and in red color are RCP 4.5, and in green color is the 8.5. So not surprising for the 8.5 for the temperature changes, you have like on the right side of the RCP 4.5, because generally more warming there. And we sort of recover, because remember in the baseline estimation for both planting date and growing season length, we have this weekly averages. So monthly frequency is not sufficient for doing this. So the way we do this is we recover a daily projected data set by adding those monthly differences back to the daily baseline climate, so that we have a reconstructed projected daily temperature and precipitation data set. And then we use this hypothetical or reconstructed data set to reback to sort of recover the growing season estimate, both the planting date estimates and the growing season length estimates, or I should say predictions, so that we can see under these different projected climate, what would be the planting date and growing season length in the future. And then this figure shows you the results. So we basically present these results in terms of empirical distribution of growing season adjustment induced by future climate, since we compute these predictions for each specific site. And those are presented as box plots. So those bars in the middle will be the median site, and the 2 boundary of the box should be the quartiles. And in red colors are planting date predictions, and in green colors are growing season length predictions. And each pair is going to be specific to a specific climate projection model. So the general pattern here is that in both RCP 4.5 and 8.5, most or the majority of these sites will experience earlier planting date and shorter growing season length. And if you look at this RCP 8.5 for those 3 models in the middle, they generate sort of the largest the shift, and the magnitude will be, for the median side, it will be roughly about 5 days earlier planting date, and on top of that, there's going to be additional 5 days or even more than 5 days shorter growing season. So it means that if you combine the two, it's going to be roughly 10 days earlier in terms of the ending of the growing season. Potentially, that could avoid some of the detrimental heat in the really hot period of the summer. So we also wish to sort of directly test or just to contextualize how do these predictions translate into yield benefits. So the way we do this is that because in our data set, we don't have direct measure of crop yields. So we utilize a yield response function that's empirically identified in this Chen et al. Paper published in June. It's also on corn yields in China over sort of a similar sampling period. So we use their yield response function, and we multiply this function with our variables in our case. So we reconstruct the necessary weather variable in their paper based on the predicted growing season change and their future climate, so that we can compare in the future with the induced growing season adjustment and without the induced growing season adjustment. What's the difference between the predicted yields of corn? So these estimates will be reflecting the yield benefits associated with these induced growing season adjustment we identified based on historical observational data. And this, if you look at the mean change under different models, all of them are positive for both RCP 4.5 and RCP 8.5. And even look at the distribution, the majority of the sites is going to experience a net or positive yield benefit. Only a very small portion of the sites will have a sort of a negative effect in terms of the yields benefit. And so in general, this growing season adjustments is going to help mitigate some of the climate change damage on corn yields in the future. But if you recall earlier, when I mentioned the work by the hypothetical simulations by Ortiz, Bobia, and Just, our estimates are far below those in their hypothetical scenarios. So it's sort of indicating that in practice, there's a lot of obstacle there, so that an optimal adjustment in growing season could be very challenging. I think I'm almost at the time, so let me just jump to the concluding remark here. So in this paper, we use a macro level data, and because we have this rich information at the macro level, this really helps us to do this sort of causal identification by using this panel estimation framework. And we look at two specific margins. One is the planting dates, and the other is growing season lengths. We sort of look at them separately. And the general finding is that higher pre-planting temperature and precipitation is going to induce an earlier planting date, and higher post-planting temperature and precipitation is going to induce a shorter growing season. And these identified impacts on growing season adjustments are very meaningful in terms of that under future climate, these are going to translate into significant yield benefits, although they are still much smaller than those under projected under hypothetical simulations. And we think our work has some meaning on or some implications on policy discussions. For example, we think that those growing season adjustments should be part of the sort of the evaluation when we start to discuss adaptation or mitigation of climate change, and especially when it comes to certain investment decisions in the farm sector. And also, we think those behavioral responses, especially related to planting, we found in this paper, sort of highlight the value of having higher quality weather forecast that can be very helpful in terms of guiding the sort of more optimal adjustment for farmers on site to do this growing season adjustment. And of course, this work has a lot of caveats and limitations. For example, the estimates we identified is based on the year-to-year variation in weather. So they're still short-run estimates by nature. But in terms of climate change impact, we're curious about long-run impact. We have some estimates in our paper, but we do not have strong evidence on that. But we think there's still something we should do or people should do to explore to directly understanding the long-run impact. And also we think the effects we identified in our papers could also be specific to context. So it may not be directly generalizable to other crops or to crops in other countries. So I think that's it. And I guess I can take some questions and yeah.
Thank you very much, Xiaomeng, for this very nice presentation, a very interesting work on a very interesting topic. We have some few questions from the floor. We will take some, but I invite everybody to put, if you have any other questions on the discussion, then Xiaomeng could answer you later, maybe, if we don't have enough time. So the first question was by David Makowski, asking whether you have interaction between precipitation and temperature in your models. And the second one was by Ping. Do you test whether growing season, GDD, has changed during the same period? So these two questions, please.
So for the first question, we don't have interaction. That's a short answer. So here, basically, we're assuming that the effect of temperature and precipitation are sort of separable. I know that's a very strong assumption. Yeah, I think something we can do in the future is to consider this interaction. I guess like in the beginning, we decided to do it in this way. It's easier to interpret the results. If we include an interaction, then both the temperature and precipitation effect, the interpretation of the coefficient will be dependent on the precipitation, like each other's level. But I think that's a fair comment. We should consider that in the future. And in terms of the question on growing degree days has changed during the same period, I'm not sure I understand exactly the meaning. So in terms of over the sampling period, there is certainly variation, and it's the variation on the same site. So here the idea is that we're really using the change in terms of within the same site over years. This measure of temperature or precipitation is going to be different. I guess I don't have a figure or table to show you this. And in addition, we have another sort of measure or analysis in the appendix, which just simply look at the sort of the trend in terms of average temperature over time since 1980 for those major corn producing regions. And we do find very strong temperature trends in terms of average temperature. I guess since growing degree days is going to have pretty strong correlation with average temperature, we will assume that it's also going to be a strong trend upward over time, over sort of 30 to 40 years over the past few decades. Yeah.
Okay, thank you very much. I have some questions, but if nobody have questions, any other questions from the participants? So I will ask my questions, waiting for other questions maybe. So I was wondering, are you sure how could you distinguish between this short-term adjustments and the anticipation? Because, for example, this year I will change my planting dates, but next year I will take into account the fact that I changed it last year. Then it will no more be in a short-term adjustment, but more anticipation from last year. So I don't know if you could distinguish these two impacts.
Yeah, I guess. Yeah, I think so here, because it's really sort of rely on this panel estimation, since we are always comparing the for example, for planting decision, for planting date, we are always comparing the pre-planting weather before the normal planting date for the same place over time, and we control for other things.
I have a question on this. What is your definition of normal date? Because it's theoretical one. It's
It's the empirical one. It's the median planting date of the same site over the sampling period. Yeah. Yeah, I guess like some of the factors could have been in the. So we are not capturing something like the dynamics in terms of decision making. I guess that's very important by themselves, but I guess they're not directly influencing our estimates on the temperature and precipitation effects in our context, because they're sort of independent. Within the variation in terms of the changes in temperature and precipitation should be, or we assume that's independent or largely independent from confounding factors that's related to sort of dynamic decision making in terms of planting. Yeah, not sure if that answered the question. Yeah.
Okay, thank you very much. We have three more questions. One from David and two from Florent. Yeah, okay. So from Florent, can you see the chat? You could answer the question.
I can see the chat. So one is, so David said that in Europe, farmers are already changing planting days and harvest days due to climate change. Is it the case in China as well? Well, I guess that's actually the motivating factor. Like we think farmers are doing this, but we did not see sort of empirical illustration of this. So that's part of the motivation of doing this work. Yeah.
Okay. The question from Florent: did you manage to find information on length of crop cycles and whether these have changed during the period you studied?
So is that related to? I'm not sure. So if
this is agronomic, I think this is agronomic points of view. I don't know if.
So double cropping, or is that related to double cropping, or I guess like. So I can say that the information we have here is so for the same crop, we have the information of the entire growing season. So starting from the planting date to the last stage will be the maturity date of the crop. And there are some information on like different specific stages within the growing season, but the data, we look at the data set and those information are not very complete. So in the end, we only use the starting point and the ending point of a growing season. So that's the information we have. And we don't look at double cropping in this case. And so we don't, if that's related to the question. Yeah.
Okay, thank you. So we have two more questions, very, very short answers, please, but maybe you can add more details on the short. So the first one was on soil. Do you take into account the soil, organic matters that in the soil? And the question from Stéphane de Cara, do you have selection bias due to the fact that you focus only on corn and you could have this switching from other crops, which could change or way of adaptation also?
So short answer for the first question is that we do not directly control for soil content here. But we have, for our results on regional heterogeneity, we think that partially reflect the different soil condition in different places. And for the last question, yes, there could be selection bias. But when we track the data set for size, we have information on corn. They did not move away for most of them, so they're still planting corn. So in that case, we don't think that's a huge issue here. Yeah.
Okay, thank you very much. So once again, I would like to thank you for your presentation and for your answers to the questions. I would like to thank all the participants also.